Now, let's make good use of all the formula we discussed by going through some examples. So let's begin with example number 1. A steel is 40 centimeters long at 20 degrees Celsius. Coefficient of linear expansion for steel is 12 times 10 to the power of -6 degree per Celsius. The increase in length and the final length when it is at 70 degrees Celsius will be dash. So the goal is to determine the increase in length and the final length. And keep in mind, when they said increase in length, they are referring to the change in length. So now let's begin by writing the formula. So the linear expansivity alpha is simply equals to L2 minus L1 all divided by L1 multiplied by the change in temperature, theta. Perfect. Now, what I would recommend while solving physics problem is that you should try and write out all the quantities given to you. This will help you to know if they are in the appropriate SI units or not. So you can always make adjustments before you begin substitution. So now we are given L1. So it's measured in 40 centimeter. So it's measured in centimeter. If you want, you can convert to meter. But for this example, we are using like that, okay? So we are measuring in centimeter. So now, the temperature, theta 1, okay, is 20 degrees Celsius. Now, our goal is to determine the change in length and the final length when the temperature increases to 70 degrees Celsius. Perfect. So therefore, theta 2 is 70 degrees Celsius. Okay. Now, well, I just changed my mind. I decided to want to convert the centimeter to meter. Okay. So therefore, 40 centimeters to meter, all we need to do is to divide it by 100. So I'm using my calculator for that, though I know that it's 0.4, but let's confirm. So 40 divided by 100, that's 0.4. Perfect. So therefore, instead of 40 centimeter, I'm having 0.4 meter. Okay. Now we can go ahead and begin the substitution. Okay. One more thing, the expansivity. Let's say for steel, it's 12 times 10 to the power of -6. Perfect. Now we can plug in the corresponding values and determine L2 and likewise the change in L. So first we need the change in L first, which is the increase in length. So now to find increase in length, that's simply this entire L2 minus L1. So first I will just cross multiply. Okay. Then I have L2 minus L1 to be equals to alpha multiplied by L1, then multiplied by the change in temperature. Perfect. So this refers to the change in length or increase in length. Now we can begin our substitution. So therefore, L2 minus L1 will be equals to alpha, which is 12, or which is this. That's 12 times 10 to the power of -6. Then multiplied by L1, which is 0.4. As we have 0.4. Then multiplied by the change in temperature. That's the difference between the final temperature, which is 70, and that of the initial temperature, which is 20. So that's -20, and we close the bracket. Okay, perfect. So finally, we can type this into our calculator. But before we do that, let's simplify the change in temperature, and that becomes 12 times 10 to the power of -6 multiplied by 0.4. Then multiplied by 70 minus 20 is simply equals to 50. And right now I'm going to use my calculator for that. Feel free to type that as well to confirm in case there might be any mistake. So raised to the power of -6 multiplied by 0.4, then multiplied by 50. Perfect. So final answer is simply equals to 0.00024. So that is our change in L. Since the length are measured in meter, then that's meter. So now we have answered the first part, which is the increase in length. So the goal now is to determine the final length, which is simply L2. So to find L2, we are going to use the same formula. But for now, let me get rid of this. But I think this should be enough. Now, since L2 minus L1 is equal to 0.00024, definitely L2 will simply be equals to 0.00024 plus L1. However, L1 is 0.4 meter, so we can add that to this to have L2. So finally, let me write that here. Finally, L2 equals to 0.00024 plus 0.4. And I'm going to use my calculator for that. I have it having 0.4. So final answer is simply 0.40024. So that is the solution to the first example. And that is how to use the formula effectively. So please always be vigilant, most especially when they said increase in length. You are not required to find L2, but L2 minus L1. So increase in length is sometimes referred to as the change in length. Also, you are very careful because sometimes they use it for temperature. On to example number 2. A metal of length 15.0 meter is heated until its temperature rises by 60 degrees Celsius. If its new length is 15.0 meter, okay, meter is there, I omitted that. Calculate its linear expansivity. So let's begin by writing out what is given to us. So a meter of length 15.0, that's L1. The initial length of the meter is 15.01 meter. Now the metal is heated until its temperature rises by 60 degrees Celsius. So here's a question for you. Is the 60 degrees Celsius, is it theta 1 or theta 2? What do you think? Pause the video and think about it. Well, the 60 degrees Celsius is neither theta 1 nor is it theta 2, but the entire change in temperature. As you can see, this is a grammar. They are trying to tell us its temperature rises by 60 degrees Celsius, which means the difference between the current temperature and what it was before is now 60 degrees Celsius. It rises by 60 degrees Celsius. So please be vigilant. That's what I'm saying. That you have to be very careful. Make sure that if you are selecting theta 1, theta 2, is the right thing you're selecting. Perfect. Now, if the new length is 15.0, so L2 is 15.05 meter, we should find the linear expansivity alpha of the metal, question mark. Perfect. So just like before, let's write out the formula. So we know that the linear expansivity is equal to L2 minus L1 all divided by L1 multiplied by the change in temperature. In most cases, or in all cases, always write the formula, as I'm very sure your teacher will assign 1 or 2 marks for that. Okay, so now let's plug in the corresponding value. Since our goal is to find linear expansivity, we have the linear expansivity to be equals to L2, that's 15.05, minus L1, that's 15.01. And everything entirely divided by L1, which is 15.01, multiplied by the change in temperature, which is 60 degrees Celsius, which I'm just going to write as 60. Okay, perfect. Now let's type that into our calculator. Well, the difference between the values at the numerator is simply 0.04. So to multiply this, I'm going to use my calculator for that. Okay, so I have 15.01 multiplied by 60. And that gives 900.6. So I'm dividing 0.4 divided by the answer. So I have the linear expansivity of the method to be 0.000044, and which can be expressed as 4.4 times 10, how many times? 5 to the power of 5, negative 5. So the unit of linear expansivity is per Kelvin or per degree Celsius. This is our final answer to the problem, and that is the linear expansivity of the method. On to example number 3. The linear expansivity of a material of a cube is 12 times 10 to the power of negative 6 per Kelvin. If the length of each side of the cube is 10 centimeters, find the area of one face of the cube and the volume of the cube when its temperature rises by 30 Kelvin. Okay, so just like before, let's write out what is given. So we are given the linear expansivity of the cube, alpha, that's equals to 12 times 10 to the power of negative 6 per Kelvin. Okay, perfect. Now we are given L1, which is the length of the cube. Okay, L1, which is the length of the cube, that's equals to 10 centimeter, which in this case I will convert to meter and divide it by 100. So 10 divided by 100, that gives 0.1, so 0.1 meter. Perfect. Now they said we are to find the area of the face of the cube when the temperature raised by 30 Kelvin. Okay, that's simply the change in temperature. The temperature raised by 30 Kelvin. Okay, perfect. So change in temperature is equals to 30 Kelvin. Okay, now the goal is to find the area and the volume. Now, are we finding the initial area or the final area? Likewise, are we finding the initial volume or the final volume? I want you to think about this. Well, notice that we should find the area and volume when the temperature raised by 30 Kelvin. So this simply means that we wanted to find A2 and V2. Are we together? We wanted to find A2 and V2 because that will be the area and the volume when the temperature is raised. So definitely before the temperature is raised, the area and the volume of the cube can be determined by the use of the length. So now let's begin. So area and volume are unknown, so the goal is to find them A2 and V2. So what will be A1? Well, from our knowledge in mathematics, a cube has all its sides to be the same, and to find one of its area, the formula that helps us to do that is simply L squared. Okay, because each face of a cube is simply squares. Perfect. Also, to determine the volume of a cube, we just need to cube the length, as that will give us the volume. So A1 is simply L squared, which is simply equals to 0.1 R squared. And squaring 0.1, we have 0.01 meter. Perfect. Now similarly, V1 will simply be equals to L cube, and that will be 0.1 cube. And if we cube 0.1, we have 0.001 meter cube. Okay, this is meter squared and this meter cube. Okay, perfect. This one is area, this one is volume. Okay, now we have A1, V1. We also have L1. Now the goal is to find A2 and V2. Now, if you could recall, there's a relationship between linear expansivity, area expansivity, and volume expansivity, and that is that the area expansivity, which is represented as beta, is equal to 2 alpha, which is 2 linear expansivity. So it means the area expansivity of the material of the cube will simply be equal to 2 multiplied by 12 times 10 to the power of negative 6. And if we do that and type that into our calculator, we should have 2 times 12 is 24, so that should be 2.4 times 10 to the power of negative 5. Perfect. Okay, similarly, the cubic expansivity or the volume expansivity gamma will simply be equal to 3 alpha, and that will be 3 times 12 times 10 to the power of negative 6. 3 times 12 is 36, which will be 3.6 times 10 to the power of negative 5. So all these informations are enough for us to find A2 and V2. So let's begin by finding A2 first. So since we know that the area expansivity beta is equal to change in area A2 minus A1, all divided by A1 multiplied by the change in temperature. Also, don't forget change in temperature is 30. So therefore, plugging in these values, we have beta, which is 2.4. First, to keep it short, I don't want the space to be consumed. Let me solve for A2 first. Because multiplying, we have beta multiplied by A1 multiplied by change in temperature to be equals to A2 minus A1. Then if we add A1 to both sides, at the end of the day, beta A1 change in temperature plus A1 equals to A2. Perfect. So finally, A2 that we're looking for will simply be equals to, now let's plug in those values. So beta, that's 2.4 times 10 to the power of negative 5, then multiply by A1. A1, we got that to be 0.01, multiply by 0.01, then multiply by change in temperature, which is 30, okay, multiply by 30, then multiply by what else? That is, okay, we are not multiplying again, we are just adding, then plus A1, that's plus 0.01. So what would that be? So let's type that into our calculator. So that's 2.4 times 10 to the power of negative 5. Okay, so negative 5, then multiply by 0.01, also multiply by 30, then we are adding 0.01, and finally I end up with 0.010072. So that will be meter squared. So that is A2. Perfect. Now on to V2. So now let's find the second volume, or the V2 of the cube. So let's get rid of this right now. Okay, I hope you are following the logic and the concept. If you have any questions so far, let me know in the comment section below. Perfect. So now we were able to define the gamma, or the cubic expansivity, as gamma to be equals to the change in volume V2 minus V1, all divided by V1, and then also multiplied by the change in temperature. So now the gamma, if we want to solve for V2 by cross multiplying, just like before, we have the gamma to be multiplied by V1, multiplying change in temperature to be equals to V2 minus V1. And at the end of the day, gamma multiplied by V1, change in temperature, plus V1 equals V2. So finally, V2 will simply be equals. So now plugging those values, we got gamma to be 3.6 times 10 to the power of negative 5, then multiply by V1, that simply equals to 0.001 times 0.001, then times change in temperature, which is 30 Kelvin over here, so that's 30, then plus V1 again, that's 0.001. Perfect. So we are going to type that into our calculator again and have our final answer. So we have 6 times 10 to the power of negative 5. Okay, oops, I would do. Then multiply by 0.001. Okay, multiply 30 and plus 0.001. Perfect. Now we have the volume to be equals to 0.00108 meter cube. So this is the volume of the cube when the temperature is raised by 30 Kelvin. And with that, we are able to provide the answers to this question. I hope you find it understandable. On to example number 4. An iron rod is 1.58 meter long at 0 degrees Celsius. What must be the length of a brass rod at 0 degrees Celsius if the difference between the lengths of the two rods is to remain the same at all temperature? Linear expansivity of iron is considered to be 1.2 times 10 raised to the power negative 5 per Kelvin, and linear expansivity of brass is equal to 1.9 times 10 to the power negative 5 per Kelvin. Pause the video and figure this question out. So let's write out what is given. So we are given the length of the iron at 0 degrees Celsius, that's at rest. Okay, so L1, I'm going to write it as Li. Okay, that is equals to 1.58 meter, and theta I is indeed equals to 0 degrees Celsius. Okay, so let me put 1 on top and 1 on top. Okay, now we are given the linear expansivity of iron that's equals to 1.2 times 10 to the power of negative 5. Okay, we're also given the linear expansivity of brass B to be equals to 1.9 times 10 to the power of negative 5. Now the goal is to determine L1 of brass, even though theta 1 of brass is equal to 0 degrees Celsius as well. Okay, but there's one very important aspect we need to pay attention to, and that is if the difference between the length of the two rods is to remain the same at all temperature. Can you digest this and figure out what it means in essence? What does that mean? What they are trying to tell in essence is that regardless of how the temperature changes, then the change in length or the increase in length of both the two substances will remain unchanged. It will remain the same. That is, L2 minus L1 at any temperature change of iron will remain the same as L2 minus L1 at same temperature change of brass. So if that is the case, then there's something that is connecting them. And what exactly it is? Here's what it is. Now, since we said their change in length will be the same, now alpha, which is for iron, that will be equals to L1 or L2 of iron, okay, and put it like this. Okay, I just want to make sure that I'm able to specify it properly. So L2 of iron, I can see my 2. Let me write it properly. L2 of iron minus L1 of iron, all divided by L1 of iron, then multiplied by the change in temperature of iron. Perfect. Also, the linear expansivity of brass is equal to L2 of brass minus L1 of brass divided by L1 of brass multiplied by change in temperature of brass. Now, if we solve for the change in length of both of them, like the difference between the length for both linear expansivities, notice that L2 minus L2 of iron minus L1 of iron will now be equals to alpha of iron multiplied by L1 of iron, then multiplied by the change in temperature of iron. Perfect. Similarly, L2 of brass minus L1 of brass will be equals to alpha of brass multiplied by L1 of brass multiplied by change in temperature of brass. Okay. Now, the goal is to set these two terms to be equal, because that is what that part is telling me in essence. The part I underlined in the first place, that's what it's telling us, that if the difference between the lengths of the two rods is to remain the same at all temperature, that is, the difference between the two lengths of the rods, okay, remain unchanged. So it means they remain the same. They are equal to themselves at all temperature. So therefore, we are going to set this and this to be equal to themselves. Okay, perfect. So that's what we are going to do right away. So to have enough space, I'm getting it off this right now. Please, I will be glad. If you have any question, let me know in the comment section below. Then I'm going to try as much as possible to explain in a more clearer way. Perfect. Now, therefore, alpha I multiplied by L1 I multiplied by change in temperature I, right, will now be equals to alpha B, that is the linear expansivity of brass, L1 of brass, then change in temperature of brass. Now, what can we say about the change in temperature? Now, since the part we are talking about that leads to this to be equal says that at all temperature, that is, at the same temperature change, at the same increase in temperature, then it means in this case, we have to consider theta, change in temperature, change in theta sub I to be equal to change in theta sub B. That is, the change in temperature of iron will be equal to the change in temperature of brass, because that is when their difference in length are equal. Because their difference in length are equal at all temperature, at the same temperature change. Are we together? So therefore, they can cancel out. So these can cancel this. Perfect. So left over is just alpha sub I, L1 sub I equals L1 sub B, then alpha sub B. Perfect. So at this point, we can plug in the values we have to solve for. The goal is to find the length of the brass. So let's solve for the length of the brass. So L sub 1 of B will now be equals to alpha sub I, L sub 1 of I, all divided by alpha sub B. Perfect. So let's plug in these values. So the linear expansivity of iron, that's given as this, as 1.2 times 10 to the power of negative 5 multiplied by, then the length is 1.58, and this is entirely divided by the linear expansivity of brass, okay, and that is this, so that's 1.9 times 10 to the power of negative 5. Perfect. So I'm using my calculator for that. So I have 1.2 times 10 to the power of negative 5, okay, then multiplied by 1.58, alright, then divided by 1.9 times 10 raised to the power of negative 5, okay, perfect. And finally, we got, let me write that here, L1 sub B to be equal to 0.997 meter, okay, it can be 998, perfect, anyhow, okay, and that's just our final answer to this problem. That gives us the length of the brass at 0 degrees Celsius. And that is the solution to this problem. On to example number 5. Steel bars, each of length 3 meters at 29 degrees Celsius, are to be used for constructing a rail line. If the linear expansivity of the steel is 1.0 times 10 to the power of negative 5 bar Kelvin. Calculate safety gap that must be left between successive bars if the highest temperature expected is 41 degrees Celsius. Well, I changed my mind. This question or this example will be converted to a practice problem. Solve this question, let me know your solution in the comment section below. If you want me to solve it, then fine, no problem. Or try your best and let me know. Alright, thank you. See you some other time. Bye for now.